So one of the best things about working with postdocs, I mean, there's so many good things, is that they actually go out and they get to be really good and famous, and then they mention that, oh, I worked with Anderson at NCAR, and everyone thinks, oh, okay, so that was really useful. And in fact, maybe it wasn't, but it's really good to have successful postdocs. You don't have to be a great postdoc advisor, but you do have to have successful postdocs. And Michael is one of those. It's really great to have you back. Haven't seen you with all the recent years' events, but it's great to have you here. So Michael's dropped by mostly just to say hello, I think, check
Yes,
on
yes.
what's going on here. Just a quick introduction then. So graduate work at Beijing University, and then off to work with Fujing Jiang at Penn State. And at Penn State, he worked both with the ENKF system at Penn State, and you'll see that legacy in what he's going to talk about today, but he also developed fundamental data assimilation techniques. Then he came here and did an ASP postdoc, spent a lot of time sitting with our group, but talked to many, many other people too. And at that point, he developed all kinds of really theoretically cool multi-scale data assimilation techniques, mostly applying those to hurricanes when you were here. And then off to NERSC, and I can never remember, there's two NERSCs, and yours is Nansen Environmental and Remote Sensing Center, hence the polar bear there, in Norway, where he has continued to use that data assimilation expertise, both on software, which we'll talk about primarily today, but also has moved into really interesting problems on small-scale ice data assimilation. So thanks so much for dropping by, and
Thanks,
take
Jack.
it away.
Yeah, and thank you all for coming. This is very nice to be here, although briefly, but I does bring a lot of old memory back to me. And I'm working in the polar region now, trying to advance the sea ice data assimilation and also a little bit the ocean model assimilation there. And so this is a side project I started to prepare myself to be able to test a lot of the new data assimilation idea in these novel models. So I call this NEDAS, the next gen Ensemble DA system. The whole effort of developing this tool is supported by two projects. SASIP is a scale-aware sea ice project. You see the cool-looking small-scale ice simulation all the way to the global model. And the other project is also very cool, is trying to simulate iceberg in the ocean model and how they move, like pick up their trajectory in the Ensemble forecast. So this is what we hope to use this software to enhance the capability within the two projects so that we can do fancy stuff. So to first motivate a bit, I quickly introduce the Ensemble DA problem mathematically. So we have some model state psi. Is going to be updated by observations phi to find the best estimate, and we use Bayesian theorem. So the observation likelihood given the state is this function, and then multiply with the prior distribution of the state gives us the new or updated probability distribution of the state. So we will use an ensemble of state given the capital of big psi, which is a matrix of size n state times NE, which is the ensemble size. And each column vector here for psi 1, for example, is the model states collected for member 1. And we use this as a sample of the PDE of the state. And then we compute the observation priors, and the big phi here, which is also vectors corresponding to the observations, phi 1, phi 2, all the way to phi NE. And these are going to be compared with the actual observation phi O to give us the likelihood function, and then all the DA problem probably can be formulated into a function in the coding sense, how to update this big psi matrix so that it characterizes this posterior probability. And the algorithm can be written as a letter A here, takes in the prior ensemble matrix for both observation and state, and the actual observation. And there will be some other parameters like observation error, standard deviation, and localization distances, inflation, etc. I kind of omitted here. So how much effort is there needed for testing a novel algorithm in real models? So this is something I ponder for a long time. So very simple models, so like looking back in the history, for the Whorf model, you might know there are some internal subroutines called nudging or FDDA, which is the 4D var. So it's earlier version of the variational method. But these are very simple implementation of method actually as a subroutine of the online model code. But when the method gets more complicated, and then we realize the whole communication actually realize we need some dedicated DA software. So there are some in the market. Dart is what's being developed here at NCAR by Jeff and the whole software engineering team. There's on the German side, we have some PDAF by Lars, and this is a different approach using some kind of LETKF, different approach to parallelize the problem. And recently there's, actually not quite recently, but this joint effort in DA integration gets into this new software trying to combine variational method with the 4D ENVAR with Ensemble method to apply to many models, hopefully, and using a lot of satellite observation. So the roadmap of a typical DA researcher, including myself, is like when we conceive some new idea, conception, and we typically use a simple programming like MATLAB, Python, Julia, whatever, and use them to create a prototype, and then we implement that method for simple models like Lorentz system or simple shallow water equation, for example. But then when we have some idea of how the method perform in comparison with some old method, we will try to implement them in either Dart, PDAF, or JEDI, so that we get connected to the real models, the real world. So then we test in real models, and if that's successful after so many years, and we get a chance to see our method in operational systems, operational use here. That's very time consuming, and especially this from prototype to implementation in big software. So I did a little bit personal survey of what's the available method on the market. So on the left-hand side, I show some DA method with increasing novelty. So the top ones are recently proposed. So see from the bottom, you have nudging, OI, 3D VAR, and the well-known ENKF. Some particle filter, non-Gaussian stuff in the DA, like you have kernel filter, rank histogram filter, and the recently proposed like beta or gamma distribution filters. Particle flow filter is another introduction, like it's a different formula of the particle systems, and this is also incorporated now recently into Dart. 4D ENVAR is a hot topic. I remember in 2015-ish, people are starting to combine the Ensemble versus the variational method. But in the market, there are also iteratives come smoother, and this Ensemble's multiple DA, and like you apply the common filter several times to form the nonlinear solution. And there's this alignment technique that also try to formulate the problem in the Lagrangian sense. Super resolution, optimal transport, these are recent proposal of new methods using combined machine learning and AI trained operators to facilitate some kind of a nonlinear mapping between a nonlinear problem space to a linear latent space. So, and there will be more AI ideas here, but the point is these Python prototype hosting these ideas currently only have implementation of simplified equations like quasi-geostrophic, shallow water, Lorentz systems, and they have this barrier, dash line here from the idealized model to the actual real models. You see the weather model, MIT GCM, the ocean model. HICOM is a very old ocean model, and CISL. NEXIM is a new ice model we're testing. Currently, it only has nudging method, for example, and also proprietary models from the ECMWF. You only have approach like 4D ENVAR in the integrated forecast system. So new ideas for nonlinear filtering, there are many, but a lot of them still stuck at the Python prototype phase. That's the point. So I want to change the story by introducing this NEDAS, so that when we have the Python prototype, I want them to be able to test in real model directly. So this is rapid testing using Python software, so that we can know early on that if some method will work or not comparing the old method and what their limitations are. So before committing resource to implementing any like this novel method in Dart or PDAF, even before operational use, we have already some filtering or screening of those methods. Like we can keep iterating on method. If it doesn't make sense, we can dismiss them early so that we don't waste any resources. And currently, the Python lab code is everyone agrees that it is easier to maintain than the bigger like Fortran or C type of programming. Jeff is shaking his head because sometimes Python has some memory treatment that might shoot people in the foot. But again, I think my point is we have a lot of library that's well maintained to help you get around some technical issues more quickly. So for example, MPI for Pi is a wrapper to the traditional MPI parallelization libraries. And also, very typically people can call NumPy, which is a function library with a lot of linear algebra, well-optimized code. So it's like you call Python, but actually what's underneath is Fortran code. So a recent invention of Numba is just in-time compilation, JIT. It also allows you to write a Python function with some internal workings, but then you compile this to run. When you run this function, it's very speed up. Also, what comes along with Python is they include the operational system integration, very well designed by software engineers there, and the error handling of running the model and checking for some status and the output of the model can be handled more easily, to my opinion, than the old-fashioned bash control scripts. And there are also a ton of open source library that can potentially contribute to the Python ecosystem, because now you have this machine learning library that's well established. The methods there are very successful to their own regard. And optimization, things like controlling the workflow, how much you run the model and stop it, and then optimize how many times you call each function. And this workflow control software, they are well developed in the community and potentially helpful. So that's why I started building this Python sister version of Dart, kind of, to see if it makes sense. Sequential data assimilation is a way to solve the 4D DA problem into a more handleable small pieces. So what I mean is that for the time step and t, so we loop through them step by step, and the DA problem after the Markovian assumption gets reduced into assimilation problem using the A function for each time step. So what it will do is to perturb the initial condition of the model states in the ensemble run. Then the model will propagate that forward in time to the next time step. And this will create some model restart file, and we use the pause restart strategy. For example, the model will dump out its current status into these files stored on disks. And potentially in the future, we may test some idea of holding them in the memory, not to write them out as files. With this state, we pass the information into the A operator. And also along it, we have the H operator that's mapping from the state space to the observation space, and that gets sent into the A as well. And also the actual observation is from the observation dataset files. And A is responsible to give us the updated model restart file, so that from which we can run the forecast model to the next time step. This is very simple to follow, but actual in the NEDAS, the workflow is quite detailed in this chart. So we still have the model restart file. It's fed into the system through some user-provided function called read var or read grid into fields prior, and that gets sent into the assimilation module. And observation data gets run through the prepare observation module, and assign observation function keeps track of the locality of the observation, and it gets written in this observation sequence data structure. Also feeds into the assimilation module. And prepare obs from state is the H operator module. I will detail that a bit later. And the assimilation module is the A operator that I showed in the previous slide, and it dumps out the posterior fields. And now you have this update module afterwards to combine information and write to the updated model restart file. And then the cycle start again to the next analysis time step. So, so module by module, I briefly introduce what happens inside of them. So for example, these modules are all written by the user, so I keep all kinds of options open. So I didn't try to encapsulate, like provide you a class where inside the class you have a certain set of methods to deal with. I don't like that idea. I think users should be able to define anything, how they choose to process the state, the observation. So I just basically you are responsible for reading this function, and if there's bugs, then you are responsible to take care of that. So read var is the function that returns a variable field, which is a 2D grid, from the restart file. And read grid is getting the 2D grid, so the model can have a different kind of projection or a different type of grid configuration. They can be even irregular mesh, like Lagrangian models, finite element methods. So I created this grid class which can support, so it can convert from many different grid types. And what it does is when you define the source grid and its target grid, inside the class there will be interpolation coefficients and rotational vector coefficients. These coefficients, I try to cache them so that when you define it and having to interpolate many different variable fields, you don't need to recompute the interpolation over and over again. So that's one fewer technical problem to deal with. And z-coordinates, I explicitly make a function here because I found a lot of the geophysical model has irregular vertical coordinate systems. So for example, weather model uses pressure coordinate. So in different horizontal locations, you would expect that the same number of layers will be situated on different actual height of pressure. And ocean systems, ocean models will have this iso peak node, which is similar to the idea of pressure, but density instead. So z-coordinate will be returning the actual coordinate, like in meters or other units, for that 2D grid defined on individual grid points. And the psi ensemble matrix now gets into this type of data structure. You have a number of ensemble members indexed by m. And horizontally, you have many grid points, so that's indexed by L with the horizontal x and y coordinates. And n here is another dimension that I introduced. It's called the field record dimension, including different z, vertical height, different time steps, and different variables. So the idea is you kind of factor the number of states into number of L's and number of N's multiplied together. And the smallest I/O task for each processor now becomes reading one field for a record N and a member M here. So you have basically a group of multiple processors, and each processor will try to grab a field from different sub-I/O tasks, and now collectively they will contribute to the full Psi matrix. Okay, and in the sense of memory, the different color here means a different processor ID. I have in this case 9 processors from 0 to 8. Sorry, it should be from 1 to 9, but I have an offset of 1 here. So in this example, I use 100 members, M from 1 to 100, and the spatial domain is cut into 9 partitions. So the L index from 1 to 9. Number of fields, I haphazardly put 1 to 4 here. So here in the bottom, you see a table of what's being stored on each processor. So P equals 1 to all the way to 9 here, storing a chunk of entire fields. This is called the field complete data. So for example, P equals 1 here will store only the first 11 members, but all the spatial partitions, so in entire fields. So this is also called state complete in Jeff's paper in 2007, because in that paper, we don't have this number of Q separation of fields. Every field is stored in the same processor, but I introduced this Q index so that you have more flexibility of how to chop up the problem into multiple processors. Okay, so the color here, basically you have P equals 0 here is responsible for storing this line, this column of states. But we need to do a transpose, because if you only have full fields for one member, there's no way to do ensemble DA, where you need to compute ensemble covariance. So what you need is instead, in the algorithm A here, is the ensemble complete. So in this case, each processor will store one row of the matrix. So part of the state in the domain, but actually all the members. So how to do this is to send chunks of data from each processor to the other processor with this gray arrow here. So 1 to 11 members, these members are needed by all the processor, but then you see that they have the spatial partition from 1 to 9, and this processor only need the first chunk, and the second processor needs the second chunk, so that parts get sent gradually into the other processors. After this, yeah, you have to transpose, and then now you can do DA. Yeah. And just shout out if you have any questions. Okay. The second module is dataset, and dataset is a similar idea. I broke the observation network into location versus record. The record has time dimension, variable names. I keep the z coordinates into the location because sometimes the observation network is irregular in space. It doesn't necessarily break into individual 2D fields. So for example, profilers, you have a lot of discrete x and y location, but then z direction, you have a continuous profile. In that case, I think the 3D structure is the smallest unit. So each processor will need to process maybe a full observation network in this sense. So LO here indexes these different locations. So observation measurements defined in the 3D space. I also introduced this random network function, which can generate synthetic observation network just to be able to make some idealized simulations in tests. And you might notice that I keep some of these miscellaneous transform functions here. These are currently placeholders. I will say a little bit more about that. I use this placeholder to introduce other components of the DA system, so that will allow you to be flexible to incorporate other ideas. This is the observation operator, the H. I think three different options is enough to encapsulate all the necessary ways observation can be created. So the first one is very general. So for a data set, you can provide an observation operator is a function which describes how to compute the corresponding observation if you are given a couple of model input states. So for example, if you have a spatial temporal integral, like those radiative transfer models, and maybe it is also a nonlinear function of the different state variables. So this ops operator can define any kind of nonlinear function for that purpose. And the second and third options are there just because sometimes we have a much simpler H operator only with some interpolation. So I think it's nice to have them there. For example, readvar can also return some non-prognostic variable as being diagnostic variables that's been observed from the model, but also defined on the 2D fields. And these can be useful so that you reuse the conversion of horizontal grid and vertical interpolation procedures in the system so that they can be processed very efficiently. And the third option is even simpler. So what's being observed is part of the state vector. So temperature, for example. And you only need to, in this case, you don't need to even read file. You can just get the state that's in the memory fields prior, and you just grab the corresponding data from the memory, and that's it. So each processor then will read an observation network with index NO and member index M. So in the same fashion of the state, we break the problem into smaller pieces. Like each processor will be in charge of getting a smaller subset of the full observation priors. So with all these prepared, now we have psi, phi-o, and phi here feeding into the transpose. And then after transpose, I created two paths for assimilation. One is batch mode. The second is serial mode. I will show that these exist because we have different flavor of the ensemble common filter with different approaches to scale up the problem. What happens in the ENKF is we make a Gauss linear assumption. So the PDF of the state now is approximated to be a Gaussian function with mean and covariance matrix. And this is how you compute the mean and covariance with the ensemble matrix. And the observation is modeled as the truth being forwarded by the H operator plus some measurement noises. And noise is assumed to be zero mean and with a covariance matrix R. And this algorithm now simplifies to do the observation forward operators, and then use this simple matrix formula, either using this matrix formula to update the ensemble matrix directly, and this is called the perturbed observation ensemble common filter. But for very big problem sizes, you don't want to perform this inverse here because that matrix is very large. So there are two strategies. One is to loop over the states and do batch assimilation. The other is like more similar to what happened in Dart. You loop over the observations and you use a singular scalar observation update equation to iteratively change the model state until the final analysis. So side-by-side comparison of the pseudocode on the left is the batch assimilation. So you do this loop over and state, and in each for each state you have this localization function rho I here. It collects the local subset of the observation and compute this matrix I plus S transpose times S. And this is basically the variance ratio, how much observation error is in proportion to the sum of the observation plus the model observation prior error. And that's basically a weighting coefficient for how much you need to trust the difference, the innovation D here. And transform matrix T here is a ensemble size by ensemble size matrix to tell how you do a linear combination of the prior model states to reach the posterior. So what you see here is this psi I here being updated by the transform matrix. And it's equivalent to the Ying if you don't have any localization rho here. You can also see that the transform matrix is identical for all the number of states. So this previous couple of lines can actually be outside of this loop. So that kind of helps you save a lot of computation. Like you can compute one transform matrix T and apply it to many, many things you want to update, as long as there's nothing too funky about the covariance matrix. So, and the cost here it scales with respect to number of ensembles, because in here you have this SVD of this matrix chi here, Kasai here, and it scales cubically with the dimension here. So we refer to this local analysis in a lot of the LETKF approaches, and it's also part of PDAF and our current ENKF system at Nansen Center. On the right-hand side is a serial approach in Dart. Instead, you loop over number of observations, and for each observation, you compute this delta E. This is the observation space analysis increment, and you see that this is the common filter approach. So you have the mean as the weighted average between the model and the observation, and this square psi here is the adjusting the ensemble perturbations. And so this will be computed by the CPU that only by the CPU that stores that number, that observation J. And what you need to do in addition is to broadcast this result to all the other CPUs so that they can perform the next two lines. So using this delta E to update the state and the observation through the covariance, and which is also localized by the localization function. And in this this formula, the cost it scales differently. So the broadcasting of this information scales to logarithm of the number of processors, and the update here scales with the number of ensemble times its dimension. So it's local state and the number of local observation here. What's worth to be mentioned is that observation increment, so this delta E here, that does not necessarily be computed only by ensemble common filter. You can also use nonlinear filtering approaches. Like in Dart, you have kernel filter, rank histogram filter, and other fancy stuff. Observation update ensemble is these two lines, and these are currently in this formula, it is linear regression. But we recently, Jeff recently introduced this probit space approach where you can do nonlinear regression, which is more catered to observation nonlinear relationship between two variables. Okay, So memory layout, it is quite, I'm quite happy to be able to grasp both kind of approaches and to unify them in the same Python software so that I can kind of provide both assimilation approaches. So on the left is it's the batch assimilation. What you stored on, so different color mean different CPU. So what you store on each CPU is a local slab of model states, and they scatter around the observation. For each state, maybe highlighted in black here, you need observation within this localization radius. So that means for CPU in the middle here, you need to include observation within this halo region that's slightly larger than the size of that slab. Okay. However, on the serial side, you just randomize stuff for each observation and state. You want the owner of that observation to broadcast the observation into many different CPU processors anyway. And so the idea of choosing the optimal memory layout is that when you draw a circle in this map, within the circle you have all different colors for both state and observation, so that the update equation can be simultaneously processed by as many different CPUs as possible to speed the computation. So now you see that instead of these chunks of domain like all contiguous in space, I kind of do this jumping. Every several grid points will be stored on both CPUs, if that makes sense. So the dark blue CPU will be a kind of a textile memory map here. And with this, I use benchmarking in the quasi-geostrophy model. In this case, has a 256 by 256 horizontal grid with 8 layers, and I use 10,000 observation. And you see this on the left-hand side, a snapshot of the truth with some vertical structure through the cross-section line here. And observation is evenly distributed in space, so they are randomized location within the domain. I use 100 members, the observation area is 0.5. This is a non-dimensional model. The prior ensemble spread is 1. I use horizontal localization distance, ROI here, radius of influence, 10 grid points, and vertical ROI is 5 layers. This is how the problem gets solved by multiple processors. If I start from 8 processor, MP equals 8, and keep increasing it until 128, you see that assimilation, the batch assimilation is shown in black and serial assimilation in gray. The elapsed time for the computation is indeed reducing very nicely. So it means that the MPI library does work, and when you throw more CPUs to the problem, it does speed up the computation as expected. And the other colors, I prepare state and prepare observation and the transpose. These are very small computation compared to the actual assimilation for this problem. And when I start increasing the model from this kind of small model to very large model, you do see the overall time spent on the problem gets increased as expected. But when you introduce more CPUs, you always have a reduce. What's noticeable is for the serial algorithm, the grid line here, it decreases very rapidly, but then it kind of plateaus a bit, because when you do the serial algorithm, you need to spend time in addition to send information around. So when there's more CPUs, you actually have a bigger overhead of communication. That kind of gets worse when the number of things being communicated are kind of increasing to a threshold when it's too penalizing to send information around into CPUs. So this is how it scales with number of processors, and I also checked how the problem scaled with dimensionality itself. So the first panel here, it fixed the number of processors to 128, but keep increasing the ensemble size from 50 to 400. And we know that the batch algorithm scales really badly. It's cubic to this NE. So you do see the black line jumps up very, very rapidly, but then the serial algorithm is almost flat, as expected. On the other hand, if we keep increasing the number of observations, so from so from 1,000 to 100,000. It's the other way around. So the batch assimilation algorithm is almost flat; it doesn't care, and the serial approach does scale linearly with that. So it's something you need to keep in mind when you have a particular problem, maybe a combination of these parameters. There's always a better or more computational efficient way to choose from the two. And in terms of an analysis result, the error, as I mentioned, the prior error is 1, the observation error is 0.5, and I increased the localization distance from 10 grid points to 200, almost no localization. And the dotted line here is the posterior analysis ensemble spread. As you see that here you have the collapse of ensemble because of too overfitting to the observation, and the error is increasing. So there's a kind of optimal localization distance for this problem. And this is as expected, and we do find some small statistically significant difference from the two approach, but I think physically what makes sense is they both have a similar performance. And consistent with previous finding that the serial algorithm is always slightly less accurate, a tiny bit of less accuracy compared to the batch simulation algorithm. I think this is due to the way when we iterate the solution from observation to observation, you kind of pre-collapse the ensemble spread for observation nearby, and then there's a chain effect, something like related to it. So the previous results also indicate that when you change the order of how you assimilate the observation one by one, it also changed the result. So there's a little bit of problem with stability here. Okay, last.
I guess I'm just gonna have to jump in real quick, is that
yeah.
It's consistent with previous findings done by people who do batch assimilation results, but it's not consistent with previous published findings from people who do serial assimilation results. I just do want to point that out. I can give you some of the papers afterwards.
That's something I want to follow up, because I have so many things to keep in track on. Yeah, I do refresh my understanding of that. Okay. So the last part of this talk is to introduce how can you do more with this Python platform. I introduced this flexibility with this miscellaneous transform functions that user can define, so that you don't necessarily do DA in the native model grid for the native model variables. You can have the capability of trying to say for observation here, you go through this T operator to this observation of phi twiddle. So in the twiddle space is something you define. Maybe it's an EOF, or maybe it's a scale component. Gaussian anamorphosis is something also interesting. So when you have a non-Gaussian distribution prior, and you map them quantile by quantile to the Gaussian space. And there are some other decomposition idea introduced by myself. When this for Python, the idea is you have these third-party filters available to do a lot of the spatial averaging, or some idea can be from third party, and it's well tested in their separate projects. But the idea is you have the capability of introducing a lot of other methods here. And yeah. And recently in our center, we are testing some idea of a super resolution. So here, this T will be in machine learning, so a network that maps from low resolution models to high resolution models equivalence. So the network will try to learn how models resolution will be represented by the low resolution model. So in action, you run the low resolution model, but then use this helper or the network here to guess what's the high resolution coefficient, counterparts will be. And then you do data assimilation, this A twiddle here in the twiddle space. Then that's a very nice idea. And other things like introduced by Japoski 2023 is to actually, we don't need to define any type of transform a priori. So you kind of just learn what should be the latent space for the approach. So for any problem that's too nonlinear in its original physical space, you have the capacity of trying to find the mapper of that space to a latent Gaussian linear space, and in which you can perform data assimilation. The update function, of course, takes the inverse of those transform, and then you can do as simple as trying to get the posterior and prior fields and take their difference and add them directly to the restart file. This is very vanilla. What you can do in more advanced sense is you can try to align features instead of having to interpolate those increments back to the original native model grid. And in the interpolation, you always lose some scale because of interpolation, truncation error, basically. And the update here is not only limited to model state variables, but I'm thinking of maybe there are some hyperparameters. For example, in Dart, you have localization or inflation factors that's also following this loop of more on this hierarchical formulation of problems. So in a sense, I want to keep everything open, all the possibilities, so that in the next few years, we have a playground to try stuff. This is the final workflow of the problem. Last but not least, I think some of the smoother approach can be replicated also in NEDAS. So I generalized the state variable psi here from only valid at one time step to being valid at multiple time steps. So this is now a 4D trajectory being represented here. So in this schematics, you run the model forecast from Tn-1 all the way to Tn plus b, and b is the lag here. And then when you do data assimilation in this dashed box, you do kind of 4D analysis, updating the initial time step Tn here. And this will be comparing the piece-by-piece differences between observation and the model state, and then using that to regress to retrospectively change any previous from n-8 to Tn. This will be updated by the transform matrix or the deltas in the dash box. So when A and B both equals to 0, and this rolls back to the traditional filter, so one step only. But if B equals 1 and A is larger than 0, this is a recursive smoother, so it's the same thing as the filter, but retrospectively, the analysis increment here will contribute also to the previous time steps. So each time step you have multiple observations being accumulated to make it more accurate. Okay, this is introduced by Geyer and Peter Yang. If B equals 1, A equals 0, this is a one step ahead. It's been done a lot in geophysical models, especially when there's uncertain parameters in the model. You want to over and over again use more future observation to constrain it. And these are very similar idea to this paper. And there are more general, smoother formulation that not necessarily B equals 1, but B equals some kind of a lag, multiple time step. Recently, there are some new paper coming out by the French group, and even more different ways to formulate the filter smoother. So I think it might be worth it to look at and compare them with the traditional filter, maybe see if they make sense. So in summary, I think I introduced NEDAS as a lightweight solution. So in the future, people can test easily the new DA methods. In the context of real models, because we're always limited by Lorenz, we want to really test early on for the new models. I show with some benchmarking that both batch and serial assimilation strategies are efficient, and they are scalable for large models. So there's nothing stopping you just to run Python version. And NEDAS has a modular design. You can kind of mix and match, change the order of operator, and kind of design your own workflow in the sense. So the code is now publicly available through our GitHub page. And I recently submitted a paper also to GEMS about this software. And if you are interested, please contact me directly. Yeah, that's it. Thanks.
Start. Are there questions in the room? Or anything online, Chris, at the moment? So I'll go ahead and ask one question. Can you go back to your lovely colored processor layout pictures?
Processor layer, ooh.
You've done it very nicely. So the primary motivation for doing the quasi-random layout in the serial assimilation is actually for load balancing.
Yes.
And so here you've used, in your QG model, you've used fairly uniform distribution. Would you have load balancing issues if you had...
if it's not spread out very nicely, homogeneously? Yeah. I think there will be to some extent, not perfectly balanced, but I think I'm hitting a sweet spot in how much you quantize the problem. So you don't want to really find the optimal balance until the size of pixels, because that will induce too much computation just to find the neighbors. And that's actually a non-trivial computation to do. And for example, I cut the domain into finite number of partitions so that I have a flexibility of counting how many local subset of observation is valid for each partition. But then you have more partitions than your number of processors. So they can be load balanced. So if the partition has almost nothing, no workload, you can bundle that with some other partition and send that to one processor. But I found that in practice, if I keep the partition size too small, almost to the size of a pixel, and that becomes inefficient, because in the transpose as well, and also in the load balanced way, the processor will have too many things to loop over to the index of each partition by partition, and it's not taking advantage of the in the memory. If you have something stored continuously, if you make a call to a computation of that chunk of memory, it's very efficient. But when you chop it up too finely and send things around, its overhead will increase. So there's a sweet spot of how much you want to do load balance, but not overdo it. That's what I mean.
Okay, anyone else yet?
Oof.
Sorry.
I have no idea.
Hopefully I didn't broke the mic, but yeah. So thanks so much for the presentation. Really nice workflow. I was wondering, so what's the overhead of coupling or like adding a new model to this framework? How much work does it require, like in terms of like people's bandwidth mostly?
So for example, I spent in creating this read var and read grid function for an ocean model. For the horizontal grid is very uniform, and if there's not too funky things to deal with, like irregularity, I spent maybe 2 weeks to test and create these functions. It's a function with some keyword arguments anyway. You define your local variable names and how to translate that into your model internal variable names. And there's something like dimensionality or some default variable arguments that you need to pass over. But overall, I feel it's not so big of an undertaking, because sometimes I found people already have those as diagnostic scripts in Python anyway. So how to read the model, get some variable, and plot them, right? So I just, for my ocean model, HiCom here, I spent 2 weeks. That's my in practice experience. And for the QG model, for example, there are also, I spent a little bit longer, like 1 month, because in the QG model, I have some small problem with interpolation there, and so it's not 1 month now, because now I have a very nice grid object, so I can very efficiently convert from grid to grid. But back then, I'm kind of limited to a same projection, so that's not ideal. So I kind of spent 1 month to create this. Using PyProj to be able to map from different projection to projection. So that's all solved. And so I would say to this point, I'm very confident that it won't take you too long to implement the model interface.
That's great. So does it do like online regrading of the model input, or how? So you mentioned the read grid, and I wasn't sure if it does like the online regrading, if like ops is like on another.
What do you mean by online regrading?
Does it like do, so do you regrade your input first so that your ops and model are on the same grids, or do you like run this and it will automatically read WRF output and then like satellite output, and then it will do like the regrading online?
The way I define is, in a model, you have a native model grid. In the observation, you have a native observation grid. And for me, analysis, I have an analysis grid, and that analysis grid can be equal to either one. You can define. So if it equals the WRF native grid, and then when we read Wolf state variables, it is transparent, so it doesn't, there's no interpolation. But when the observation comes to the analysis grid, there's some interpolation. When you have multiple model components defined on different grid, and the common idea is to have an analysis grid that's close enough to both. And then when you map from different models to the same analysis grid, there's a minimal amount of interpolation you need to do. And the interpolation, sometimes when we have this weird CISL model, which is for each member, there's a moving mesh. The mesh actually moves along with the ice features. So for different members, the triangles now are not co-located in space. So I have to use a slightly higher resolution analysis grid that's common to every member. So when I interpolate over, I can do ensemble DA in the analysis grid. Yeah. So it can be transparent, and it can be as complicated as a DA problem itself with a lot of interpolation. Yeah.
Thank you.
Thanks.
I don't think you did. Right now it's in one piece. Anyone else in the room right now? Anything online yet, Kristen? Let me ask another question. So if you can go to your scaling figure, I think it was shortly after the one we were before you.
This one
So
or this one?
Back, that one.
That one.
So I guess my question is, what hardware are you actually running on here? So certainly in Dart sequential stuff, serial stuff, we have not historically run into applications that have this upswing that you're seeing.
Yeah.
And I can create them with very, very large numbers of observations without doing anything else.
I think that's additional overhead in Python when I try to do the MPI communication. So when Python try to call function too often in the for loop, for example, it's penalized differently as in Fortran compiled code. So and I see the problem gets worse when I have multiple computers, and in between I also suffer sometimes from network issue. Like in your paper, you have this low latency approach, but sometimes the latency is not ignorable. The machine I tested is a quite standard supercomputer with 128 cores in each compute node, and the CPU is about 1.5 gigahertz. And yeah, it's quite typical standard stuff. Yeah, it's a Norwegian Sigma 2 class. Sigma 2 is the company name.
And I guess so your comment about Python versus Fortran with MPI may be the relevant thing, because certainly across a wide array of platforms, we haven't seen this type of behavior with such low processor counts for problems like this. So
yeah. Yet to be tested more by other people, but on other platform, I guess. Yeah.
Okay, last chance in the room, online. Well, that's really, really amazing amount of work, because I know you're just doing this on the sides too, so really nice. So thanks for presenting it.
Thank you, Jeff. And thank you very much.